Okay, good morning everyone. How are you all doing? Good? Cool, yeah, I hope your week is going well so far. So what we're gonna go through today is we'll finish up the divide and conquer sorting algorithms where we talk about merge sort and quick sort. And then we'll move on and look at a really interesting kind of sorting algorithm called non-comparison based sorting algorithms. Where we don't perform any comparisons. So that's really interesting. How do we sort things without actually comparing them, right? So yeah, when we left off on Tuesday, we were looking at the analysis of the merging part of merge sort, right? So we already looked at how we split the array into two halves, right? We're not physically creating two copies of the array. What we're actually doing is we're just calculating the midpoints of the array, like the middle index, and then we're just calling the function recursively on the left half and then the right half of the array. Okay, and the time complexity of the splitting is just 0.1 because of that, right? We're just performing a calculation. Meanwhile, merging is the tricky part of merge sort, right? How it works is we look at the two halves of our array, and we begin by comparing the first element in each of the halves, right? So the smallest element in each half. And we take the smaller one and we put it into our temporary array, and then we just repeat that until we've filled up the temporary array, right, with the sorted elements. And then we just copy the elements back. So in our analysis, we concluded that the time complexity of merging is O(n), right, where n is the total number of elements in both of these subarrays. Okay, so what that means is that when we merge two subarrays of size 1, as in this diagram over here, right, that takes two comparisons, right, or two steps. Same for when we're merging the 4 and 7, the 1 and 3, the 2 and 6, right? When we merge these two subarrays of size 2, that takes 4 comparisons, right? And then same thing for merging 1, 3, and 2, 6, right? And finally, when we merge the two arrays of size 4 into one sorted array of size 8, that takes at most 8 comparisons. Okay, so that's the cost of merging. And this is going to be really important for analyzing merge sort as a whole. Right, so just keep this in mind. But first we'll look at the implementation of merge sort. Right, so merge sort as a divide and conquer sorting algorithm, it's recursive. So you see that we call merge sort inside merge sort. Right, so what does this function do? Well, first, as with any recursive function, there's a base case, right, where we check if low is greater than or equal to high, right? So can someone tell me what this is checking for? What does this mean? Yeah?
If the sizes are equal, so like your array is empty.
Yeah, so if the array is empty, if that's the case, then low would be greater than high. It's also checking for if the array has only one element, right? So if low is equal to high, then that means there's only one element in the array, and that means it's already sorted, so we just return. Okay, and then, all right, if the base case isn't satisfied, then we calculate the midpoint by taking low plus high and dividing by 2. And then we call merge sort recursively to merge sort the left half and the right half of the array. Okay, and after we've merge sorted both halves of the array, we now need to merge the two sorted halves into one sorted array. So that's what we call merge. Okay, and so if we want to understand merge sort, we really just want to see how the merge function works, right? Because that's where most of the logic is. So here it is. Okay, so what does it do? So first of all, we saw that merge sort needed a temporary array, right, to store the sorted sequence before we copy it back. So here we call malloc, right? We call it and give it the size of the array that we need, right? So how big does our temporary array need to be? Well, it needs to be high minus low plus 1. It needs to have space for that many elements, right? And then we times by the size of the item, because the item might be an int, it might be a char star, it might be a struct. Okay, and then we create 3 indexes, right? I, j, and k. So I and j are going to keep track of where we are up to in each of the halves, right? So what's the next elements that we should be comparing in each of these subarrays. And k we use to keep track of where we should insert the next elements, right, into our temporary array. Right, so k is initialized to 0. And in this while loop, we're comparing an element from the left subarray, an element from the right subarray, and whichever one is smaller, we copy it into our temporary array. Okay, so le here is our function or macro for checking if one item is less than or equal to another item. So if items I is less than or equal to items j, then we copy items I into our temporary array. Okay, and here we're performing I++ and K++ on the same line. So what this does is, first so the effect of this statement is that first it'll do temp k equals items I, and then it'll increment I, and then it'll increment k, right? Or it'll increment k and then increment I. So that's what happens if you put the plus plus after the variable, right? So if you put the plus plus before the variable, then it will increment the variable first and then do the statement, okay? Yep, and so if items I is not less than or equal to items j, then we copy items j instead into our temporary array. Right, so notice that this comparison is a less than or equal to, right? That's because if the items are equal, we want to take from the left subarray to ensure that the algorithm is stable. Okay, and this while loop keeps on going until we've used up all the elements from one of the halves of the array, right? And then we just use these 2 while loops to copy the items from the half that we haven't used up. Okay, so while I is less than or equal to mid, we copy all the remaining items from the left half. But if we've already used up all the elements from the left half, then the second while loop here will copy all the remaining items from the right half. Okay, and then after we've copied all the elements into our temporary array, we copy them back into our main array with this for loop. Okay, and after that, we need to free our temporary array. Okay, so does anyone have any questions about this code? Yeah?
Couldn't you do it directly in the items array so you don't have to place the space on having a temporary array?
Good question. So the question was, can't we merge the items into our items array instead of creating a temporary array? So the problem with that you'll find is that if you try to merge the items into the original array, you might end up overriding items that you haven't merged yet. And yeah, that will cause you to lose items. Yeah, so that's why you need a temporary array. Okay, so let's, oh yes, another thing is that notice that we're mallocing a temporary array every time we call the merge function. So one possible improvement is you could just merge, you could just malloc one giant array at the beginning and then just reuse that, so you don't have to call malloc every time you merge, right? So And then you can just pass that temporary array into the merge function. Yeah, so that's one way you can improve this. Okay, and here is the diagram that I showed you before again. But here we're going to kind of use it to analyze merge sort. So what's the time complexity of merge sort? Well, there are two things we have to consider, right? There's the splitting and the merging, right? So we're going to total up the cost of splitting, right? How many times do I have to split? And then we're going to total up the cost of merging, right? And then figure out the cost, right? So first of all, the splitting, right? That's the easy part, right? Every time we split the array, that's going to be O1, right? But how many times do we have to split the array, right? If we have an array of size n, how many times is the algorithm going to split in total? Anyone have any ideas? Sorry? Log n. So that's a good guess. So that's the number of levels of splitting we have to do. But it isn't the total number of splits. So any other ideas? So the total number of splits is n minus 1. Yep, so you can look at this array for example. So if we have an array of size 8, we have to split 7 times. And you can count it yourself. So 1, 2, 3, 4, 5, 6, 7. Right, so 7 splits. And the reason is that we start off with an array of size. We start off with a single array, right? And then at the very bottom, we have n arrays of size 1, right? And every time we split, we're creating a new array, essentially, right? So how many splits do we have to do to end up with n arrays? That's n minus 1. Okay, but yeah, the number of levels of splitting we have to do is log base 2n, right? So if you think about how many levels of recursion there are going to be, that's log base 2n. Okay, and that means the total cost of splitting is On, right? Since we're doing n minus 1 splits, and each split is O1. Okay, when we merge, right, we have to consider how many times we merge, and for analyzing merge sort, we want to consider the cost of merging across each level, right, across each row. Okay, so remember when we analyzed merging, that the cost of merging is like On, where n is the number of elements in the two subarrays, right? So that means the cost of merging these two subarrays, the 5 and 2, is around 2 steps, right, or 2 comparisons. And same for the 4, 7, the 1, 3, and the 2, 6, right? But if we sum up the cost of merging across the entire level, right, that's going to be n, right, in total, right, where n is the original size of the array, right? So for this array, we have 8 elements. The total cost across this entire level, right, is 8 steps, right, or 8 comparisons. Okay, and same for the next level, right? On the next level, we're merging 2 arrays of size 2 into an array of size 4. That takes 4 comparisons. And over here, we are also merging 2 arrays of size 2 into an array of size 4. Right, that's 4 comparisons, but across the entire level, that's going to be 8 comparisons, right? Or for a general array, that would be n comparisons across the entire level, right? And for the final step, where we're merging 2 arrays of size 4 into an array of size 8, right? That again takes 8 comparisons, right, across that entire level. Okay, so since across each level of merging, we're performing about n steps, right, or n comparisons, and we have log base 2n levels of merging, right? So that's the number of rows in rows of merging in this diagram, then the total cost of merging is n log n, right? So O n log n. Yeah, and so the splitting costs big O of n, the merging costs n log n, so the n log n dominates. And that's our final time complexity. Okay, and notice that merge sort kind of performs the same kind of steps, right? The diagram doesn't change regardless of whether the array is sorted or not. Okay, so even if the array is sorted, it still does the splitting and the merging exactly the same way. Okay, so that means merge sort is going to be n log n if the array is sorted, if the array is randomly sorted, if the array is reverse sorted. Okay, so that tells you about the adaptability of merge sort, right? It's not adaptive. Okay, so yeah, okay, so this is kind of what I mentioned, right? So we have log base 2 n levels of merging. The same operations happen at every level. Okay, and each level requires up to n comparisons. Okay, so another way you could actually analyze merge sort is you use a technique called the master theorem, but that's out of the scope of the course, right? So there's something called the master theorem, which you might learn in COMP2521. And it lets you analyze algorithms, analyze like divide and conquer algorithms that have this kind of runtime. So that have a runtime like this, where it's like the cost of merge sorting an array of size n is equal to the cost of merging two arrays of size n on 2, right? Because you're recursively merge sorting both halves, plus n, right? So n here is the cost of merging the two subarrays back together. Okay, so you end up with this kind of recurrence, and then the master theorem helps you solve this recurrence. Okay, but it's not required knowledge for this course, but I just decided to put this here. Okay, and for the properties of merge sort, so it's stable, right? We talked about why it's stable, because if you're comparing two elements that are equal, you take the element from the left subarray. And merge sort is non-adaptive, which we also talked about, so it performs the same kind of steps regardless of whether the array is sorted or reverse sorted or random. Okay, and merge sort is not in place, right? Because it uses a temporary array to store the sorted sequence during the merging. Okay, and in addition to using up to ON space, it also uses stack space, right? Because it's a recursive algorithm, right? And the amount of stack space it uses is log n, right? Because there are log n levels of merging, right? So number of function calls to merge sort that are going to be on the stack at any point in time is going to be at most log base 2n. Okay, and then we can also talk about merge sorting linked lists, right? So how it works is quite similar to how it works on arrays, right? We first split the array into two halves, like two roughly equally sized halves. Then we recursively merge sort both linked lists. And then we merge the two sorted lists back together. Okay, so that's how you would merge sort a linked list. And the merging two sorted lists into one sorted list is a nice practice exercise for linked lists. So that might be on the practice exercises page. If not, you can you could try and write it up yourself. Okay, yeah, so I can slow down a little bit. Yes, I can do that, but you could help me by indicating what you're confused about as well. Yeah. Okay, and then we also have something called bottom-up merge sort, right? So the merge sort that I showed you is recursive, right? But it turns out there is another way of implementing merge sort, which is non-recursive, right? So how it works is, I'll just show you the diagram, but here's a description of it. But here's how it works, right? So at the start, what bottom-up merge sort does is it treats our array as containing n sorted subarrays of size 1, right? So it says that, okay, each of these elements in our original array is a sorted array of size 1, okay? And then what it does is it gradually merges, so it takes these two arrays of size 1 and it merges them into an array of size 2, and it does this all the way down the array. So it takes pairs of arrays of size 1, right, and then it merges them into sorted arrays of size 2 like we have here. So we have AS, OR, and here we have TI, but if we sort those it becomes IT, right? And with NG that becomes GN, and EX, and EM, and LP, and then AR, okay? And then next, it takes the two sorted arrays of size 2, or it takes pairs of subarrays of size 2, and then it merges them into arrays of size 4, right? So for AS and OR, it merges those into AORS. For ITGN, it merges them into GINT, and so on, right, all the way down the array. And then it keeps doing that, so it merges merges pairs of arrays of size 4 into arrays of size 8, and then finally it merges these two arrays of size 8 into one array of size 16. Okay, so it gradually merges longer and longer sorted runs into bigger sorted runs. Okay, and here's the implementation of bottom-up merge sort. So, like with the sorting algorithms that we talked about, it takes in an items array and a low and a high. And this outer for loop, right, this m variable is the lengths of the runs that it's merging together, right? So initially, the length of the runs are just 1, right? So we have n arrays of size 1. And notice that every iteration is multiplying by 2, right? Because in the second iteration, it's going to merge the two arrays of pairs of arrays of size 2, and then it's going to merge pairs of arrays of size 4, and so on. Okay, and what the inner for loop does is it performs one of the merging steps, right? So it goes all the way down the array, and it takes the pairs of arrays and merges them into bigger arrays. Okay, and inside this inner for loop, we have a calculation here, min I plus 2 times m minus 1 high. So the point of this, so you don't need to worry too much about this, but this is just to take into account the situation where the size of the array isn't a power of 2, right? And we might need to chop off one of the runs earlier. Okay, so that's just that calculation. And then we call the merge function, right? Which is the same as the merge function we used in top-down merge sort. Okay, so the reason why this is called bottom-up merge sort is that if you look at the diagram, right, with top-down merge sort, we're kind of starting from the top of this tree, right? So we're starting by trying to merge sort the entire array, and that gets recursively broken down into smaller and smaller subarrays. Okay, with bottom-up merge sort, we're not starting from the top, right? We're starting from the bottom, right? So we're merging these two together, right? These two together, these two together, these two together, and then we're merging progressively larger and larger subarrays until we end up with one full subarray. Okay, so here are the steps again, just to answer the question in the chat. Yep. So the slides are also on the course website if you want to check it out. But yeah, in terms of analysis, the time complexity is the same as top-down merge sort. Yeah. But the advantage of bottom-up merge sort is that you don't have the overhead of recursion, right? Because bottom-up merge sort doesn't perform any recursion. It just calls the merge function, which isn't recursive. Okay, and in fact, you could, so you could actually analyze, or you could time merge sort. So I have a top-down implementation and a bottom-up implementation. And if you run these two, or you time these two, it turns out that bottom-up is slightly faster. Okay, but they do have the same time complexity. So what I do is I'll generate 10 million elements, right, randomly sorted, and I will pass them into top-down merge sort. And I'm just going to ignore the outputs of the merge sort because all I care about is the time. Right, so this is going to take about 5 seconds because I've timed it before, so it took about 4.51 seconds. Okay, and then if I do it again, hopefully the time should be similar. Okay, and then what I can do now is time bottom-up merge sort, and if I get the same results as I did yesterday, it should be slightly faster. Yeah, 4.18 seconds. Okay. So it's slightly faster. It's faster by a constant factor, right? The time complexity is still the same because, well, the time complexity is still the same because the number of times you have to do the merging is the same, right? The number of passes you have to make through the array to merge is still log base 2n, right? And you have to go through the entire array on every pass, right, which is n. So n times log base 2n, that gives you n log n still. Yeah. Okay. So that's merge sort, and that's the end of merge sort. So does anyone have any questions about merge sort? Okay, so yeah, so merge sort is a really cool algorithm, and so is quicksort. So quicksort is also a divide and conquer sorting algorithm. It's recursive, but it works in a very different way. So let's see how it works. So it was invented all the way back in 1959. So these algorithms are pretty old. Let's see how it works. Okay, so how quicksort works is it uses items called pivots, right? So first of all, it chooses an item from the array to be a pivot. Okay, and the purpose of the pivot is it's going to rearrange the array, right, so that all the items to the left of the pivot are smaller, right, or less than or equal to the pivot, and all the elements to the right of the pivot are greater. Okay, and after it has rearranged the array in that way, so after it's partitioned the array, it's going to recursively sort each of the partitions. Okay, so here's a kind of diagram of how it works, right? So it's going to choose an element to be the pivot. Here we've just selected the leftmost element. Right. After we partition the array, the pivot is going to be somewhere in the middle of the array. So it's going to be somewhere in the array, but what's guaranteed is that everything to the left of it is going to be smaller than or equal to. Everything to the right of it is going to be greater than or equal to. Right. And then these halves of the array, they're not necessarily even, right? So they're not necessarily equally sized. That's because we don't know. So we don't know how large the pivot is, right? So if the pivot happens to be the smallest element in the array, then you're going to end up with a really uneven split, right? Because everything is going to end up to the right of the pivot, right? But if the element you choose to be the pivot happens to be the median element, right, then you're going to end up with very evenly sized subarrays. Okay, and then after you've partitioned the array, you then recursively quicksort both halves. Okay. And then the array will be sorted. Okay, so we can compare this a little bit to merge sort, right? With merge sort, we perform the recursion, right? So we merge sort both halves recursively, and then we perform the merge, right? So the computationally heavy part happens after the recursion, right? With quicksort, we first partition the array, and then we recursively quicksort, right? So the computationally heavy part of partitioning happens before the recursion. But the nice thing is that after you recurse, the array is sorted, right? Don't need to do anything after you recurse. Okay, so the tricky part of quicksort is partitioning. So how do we actually partition the array? Okay, so first of all, what we'll assume is that the pivot is stored at index low. So the pivot is the leftmost element of the subarray. And if we do choose another element to be the pivot, then we can just simply swap it so that it ends up being the leftmost element. And then what we do next is we create two indexes, right? So one index points to the start of the array. So by start of the array, I mean the element after the pivot. And then we create another index to the end of the array. And then with these indexes, what we're going to do is we're going to keep incrementing the left index until we find an element that's greater than the pivot, right? So this element doesn't belong on the left side of the array, right? It kind of belongs on the right side of the array, right? So we keep incrementing the left pointer until we find such an element, and then we decrement the right index until we find an element that's smaller than the pivot, right? And this element doesn't belong on the right-hand side of the array, it belongs on the left, right? So now that we've found two elements, right, one which doesn't belong on the left-hand side, one which doesn't belong on the right-hand side, we swap them. Okay, and then we repeat this until the two indexes meet in the middle. Okay, and then finally, we need to swap the pivots into the middle of the array. Because remember, we kind of left it at the start of the array. So we need to move it into the middle so that everything to the left is smaller, everything to the right is bigger. Okay, so here are some examples of partitioning to hopefully make it clear how it works. Okay, so here we're going to take 4 as the pivot, and then we're going to create 2 indexes, right? One that points to this element and one which points to this element 5. And we're going to increment the left index until we find an element that's greater than the pivot. Right, so if we increment it, then we will find a 7 here, which is greater than the pivot. So we stop incrementing the left index, and then we start decrementing the right index. Right, so now we decrement the right index. Right, so 5 is greater than the pivot, so that's fine. But 2 is not greater than the pivot. So now we take these two elements and we swap them. Okay, so we swap them. Okay, and now we just repeat. So we increment the left index. So 2 is smaller than the pivot. 3 is smaller than the pivot, but 6 is not smaller than the pivot. And now we switch over to the right index. So 7, that's greater than the pivot, right, but 1 is not greater than the pivot. So now we swap these two, and we keep going. So 1, so now we increment the left index again. So 1 is smaller than the pivot. 6 is not smaller than the pivot. But now the two indexes are now pointing at the same index. Okay, so now we stop and we swap the pivot into the middle of the array. Okay, so depending on where the two indexes meet in the middle, we might end up swapping the pivot with that index or the index to the left of it, right? So, so you have to be careful about what you swap the pivot with. In this case, you don't want to swap the pivot with the 6, right? Because then you're going to have an element larger than the pivot, 6, to the left of the pivot, right? Which means you haven't partitioned the array properly. So what we have to do here is swap the 4 with the element to the left of where the indexes met in the middle. Right? So we swap these two elements. Okay, and now we've properly partitioned the array. Okay, so yeah. Okay, and now we're done, right? So 4 is in the middle, everything to the left of it is small, and everything to the right is bigger. Okay, so in this case, we happen to choose a pretty good pivot, right? So we partitioned the array pretty evenly, but here's an example of where we don't partition the array very evenly, and that's because when we choose the pivot, we don't actually know how large or small it is relative to the other elements, right? So it is kind of based on luck whether you choose a good pivot or not. But there are techniques to try and choose a better pivot, and we'll cover those later. But here's an example of a bad partitioning. So we chose 1 as the pivot, and 1 is the smallest element in our array, right? So we kind of can see how this is going to end up. Right, so we create the two indexes like before, and we try to increment the left index, but we immediately find an element which is greater than the pivot. Right, so we stop. Now we decrement the right index until we find an element that's smaller than the pivot, and it turns out we won't find such an element, right, before the indexes meet. And what do we do now? Well, we have to swap the pivot into the middle of our array. I mean, in this case, it's not really the middle, but we end up swapping the 1 where it should go so that everything to the right is bigger, right? And then it just ends up where it was before. So yeah, it just stays there. And now we're done, right? So everything to the right of the pivot is greater, right? And there's nothing to the left of the pivot. Okay, so that's kind of the worst case of partitioning, right? Because now we kind of have to recursively quicksort all of these elements, right? And we started off with an array of size n, and now we have to merge, quicksort an array of size n minus 1. right? Meanwhile, before, we had a pretty even split, right? And we ended up having to quicksort 2 arrays of size n on 2, roughly. Okay. So there's a question asking what if the pivot value is repeated. So if the pivot value is repeated, then so it's fine because what partitioning should do is all the elements to the left should be less than or equal to the pivot, and all the elements to the right should be greater than or equal to the pivot. So it's fine if there are values in the array which are equal to the pivot. Okay, so let's analyze partitioning. Okay, so partitioning is big O of n, right, where n is the number of elements, so n is the size of the subarray. Okay, and why is that? That's because think about what we're doing here. Right? We're just creating 2 indices, and combined, they're going to be scanning all the elements of the array, right? So we're performing about n comparisons, right? And then we're also performing some swaps, but the number of swaps we're performing is at most n on 2, right? Yeah, so we perform about n comparisons. You can try and visualize that, right? So we're comparing every element to the pivot, right? And then in terms of number of swaps, we're performing at most n on 2, because the most amount of swaps you can do is like if you just swap these 2, and then you move the indices together 1 step, and then you have to swap again, and then you move them together 1 step again, and then you have to swap again, and so on. So n on 2 swaps at most. Okay, and this will be relevant for analysis. So just keep this in mind as well. Okay, so here is the implementation of quicksort. So I've called this naive quicksort because we're always selecting the leftmost element as the pivot. Right, and we'll look at some variations of this later. But notice that it's recursive, right? And we have a base case, right, where we're checking if the array is either empty or has size 1. Okay, so if that's the case, then we just return because the array is already sorted. And otherwise, we call the partition function, right? So that function will partition the array around a pivot, and importantly, it returns the index of the index where the pivot ended up, right? And that's because when we choose the pivot, remember, we don't actually know we don't know where it's going to end up in advance, right? So we have to return that so that when we recurse, we're recursing on the right bits of the array, right? So when we recurse, we recursively quicksort between index low and pivot index -1. So that's all the elements left of the pivot. And then we recurse between pivot index +1 and high. So that's all the elements to the right of the pivot. Okay, and here's the partition function. Okay, so it's selecting the leftmost element as the pivot, right? That's items low. And then it's creating 2 indices, L and R, right? L starts off at low +1, R starts off at high. And then this while loop is checking that the 2 indices haven't met in the middle yet. Right? And inside this while loop, we have two other while loops. So this while loop here increments the left index, right, while the item at that index is less than or equal to the pivot. The second while loop decrements the right index while the element at that index is greater than or equal to the pivot. And then once the two indices meet, so if L is equal to R, right, then it breaks out of the loop. Otherwise, it swaps the two items. Okay? And after the while loop, right, remember we need to swap the pivot into the middle of the array. And remember that the index that you swap the pivot into might be equal to the index that the two pointers met in the middle, or it might be the index to the left of it. Right, so this if statement is just to check whether you need to swap with that index or the index to the left. Right, and then you perform the swap. Okay, yeah. So does anyone have any questions about the implementation? Okay, so if you're wondering about this if statements, so it might be a little confusing, but you can refer to the example that we went through here. So in this case, remember we needed to swap with the element to the left, right, of where the indices met. So you can walk through this example and see why that if statement is necessary. Okay, so now let's look at the analysis of quicksort. Okay, so in the best case, right, quicksort is gonna choose the best pivot every time, right? What I mean by the best pivot? Well, if the pivot happens to be the median element, right? So if we choose the median element for the pivot every single time, right, then we're going to end up with very equally sized partitions at every recursive step, right? Like I've shown in the diagram here. Okay, so we have very equally sized partitions at every step, every level, and that means, like with the merge sort diagram, we have log base 2n levels of recursion. Okay, and remember that the cost of partitioning is equal to the size of the subarray that we're partitioning, right? So during the first partition, right, that takes about n comparisons in total, right? And in the next level, so where we have two arrays of size roughly n on 2, right, partitioning the left, partitioning this array takes about n on 2 comparisons. Partitioning the right subarray also takes about n on 2 comparisons. But in total, across the entire level, we're performing roughly n comparisons. Right, so across this level, it takes about n comparisons. And since we have log base 2 levels of recursion, the total cost, the total number of comparisons is roughly n log n. Okay, so that's the best case of quicksort. Now, how about the worst case? Right, in the worst case, we choose the smallest or largest element for the pivot. Right, remember, we don't really know how good our pivot is in advance, right? So if we're really unlucky and we always choose the smallest or largest element for the pivot, then every time we partition, we're going to end up with a subarray of size n minus 1, right, that we have to recursively quicksort. Okay, and at each level, right, on the first level, we had to perform roughly n comparisons. On the next level, we have to perform roughly n minus 1 comparisons. On the level after that, we have to perform roughly n minus 2 comparisons, and so on, right, all the way down. And how many levels of recursion are we going to have? It's going to be roughly n, right? Because every level, the size of our array that we're quicksorting is one smaller than the level above. Okay, so if we add up all the comparisons that we have to do, right, n plus n minus 1 plus n minus 2 plus n minus 3 plus all the way down to 1, the total of that is going to be in the ballpark of n squared, right? So big O of n squared. Okay, so that's the worst case. Now, for the average case, right, we're gonna assume here that so the way we can analyze the average case is by taking randomly ordered arrays, right, and then timing how long quicksort takes. And if you do that, then you'll end up with something resembling n log n. So we could actually try this. So here I'm gonna compile all these sort programs, but what I'm interested in is naive quicksort. So I'll just generate, let's say, we'll start with 1 million elements at first. So we'll generate 1 million numbers sorted at random, and then we're going to pass them into our quicksort program, and I'm going to time it. Okay, so time naive quicksort, and I'm going to ignore the outputs, just like before. Okay, so it's taking about 0.45 seconds. Okay, and if I double the size of the array, it should take about twice the amount of time, but a bit longer, right? Because it's because the time complexity is n log n. So it's taking 0.95 seconds, which is about right? It's a bit more than double the amount of time. Okay. Yeah, and the reason the average case, another reason that it's n log n is that the chance of the worst case, so if the array is randomly ordered, then the chance of us choosing a bad pivot repeatedly is very low, right? So yeah, that's a kind of hand-wavy way of explaining it, but you can also show it empirically, like I just did. Okay, so yeah, that's the analysis of quicksort. So what we'll do now is we'll take a 5-minute break, and then we'll finish off quicksort, and then we'll talk about non-comparison based sorts, right? Okay. Okay. Okay, so let's get back into it. So it is 5 past. So what we're going to do now is we'll finish up quicksort by talking about its properties and some variants, and then we'll move on and look at non-comparison based quicksort, non-comparison based sorting algorithms. Okay, so in terms of stability, right, quicksort is unstable, and that's because it, like selection sort, it performs long-range swaps, right? And that means it is likely that you'll end up swapping an element over another element that has the same key, okay? And that would make it unstable. In terms of adaptability, right, quicksort is non-adaptive, right? And why is that? And that's because the average case of quicksort is n log n, right? If you have a randomly sorted array, then quicksort is going to be n log n. And if your input is sorted and you use the naive strategy of choosing the leftmost element as the pivot, right, then in fact quicksort is going to be n squared, right? Because your array is sorted and you're always choosing the smallest element as the pivot, and you're going to end up with a scenario like this one. Okay, so interestingly, sorted input is a bad case for this variant of quicksort, right, which is pretty interesting. And it's important that you don't confuse best case with a sorted array, right? Those two things aren't necessarily the same, right? The best case for a sorting algorithm isn't necessarily when the array is sorted, right? It might be when the array is randomly sorted, as is the case for quicksort. Okay, so make sure not to confuse the two. And finally, quicksort is an in-place sorting algorithm, right? This is unlike merge sort, where it needed a temporary array, right? It does all the sorting within the array itself, right? And even though quicksort is in place, right, it doesn't mean it takes up O1 memory, right? It does use stack space because it's a recursive algorithm, right? And in the worst case, it's going to take ON stack space, right? So in this case here, you'll end up taking ON stack space, but on average, you're going to end up taking log n stack space. Okay, so quicksort is one of those algorithms where the average case is the more realistic time complexity to consider, right? Where the worst case isn't actually very likely. So the worst case is quite unlikely in this case, if your array is randomly sorted. Okay, but yeah, we talked about some of the issues about quicksort, right? Where choosing a bad pivot can end up with quicksort being really inefficient, right? So we want to choose a good pivot, which is the median value, right? But we don't know whether the pivot we chose is the median or not, right? So we don't, we can't decide to choose the median value for the pivot in advance. And if we choose a really bad pivot, then that will lead to the worst case, which is big O of n squared, time complexity. And that's why always picking the first or last elements, the leftmost element or the rightmost element as the pivot, is not a very good idea, right? Because first of all, if your array is already sorted, and that can be a pretty common case, right, in real life situations, having a sorted array is a worst case, right? Having a reverse sorted array is also a worst case, and yeah, you're going to end up with quicksort taking quadratic time O(n) squared. Okay, so to deal with this problem, there are other variations of quicksort that can choose the pivot in a different way. So the first one is called median of 3 partitioning. Right, so how this works is instead of just always taking the leftmost element as the pivot, we consider 3 values from the array. We consider the leftmost element, the rightmost element, and the middle element. Right, and we choose the median of those values to be our pivot. Okay, so that's very nice for a sorted array, because if we use the median of 3 partitioning strategy, right, and we have a sorted array, then the median array, the median element is going to be the middle value, right? So we'll end up choosing that element as our pivot, and we'll end up with very equally sized partitions, as in this diagram. Okay. So how it's implemented is we sort these 3 elements so that the median of those elements is at index low, right? And then remember back to the implementation of partition where it takes the leftmost element as the pivot, right? Then we can just reuse that function, right? Because our median value is now at index low. Okay. So here's an example. Okay, so we have the leftmost element as 2, the rightmost element is 5, and the middle element is 8. Okay, so the median of these values is 5. So we're going to rearrange these 3 elements so that the 5 is on the left. Okay, and that's it. And now we can call the partition function on this array, and it'll take 5 as the pivot. Okay, so here is how you would implement it. It's only a slight change from naive quicksort. Right? Before we call partition, we're just going to call our median of 3 function, and in the median of 3 function, we're going to just rearrange those 3 elements. Okay, so that's the median is at index low. Okay. Yeah, so we're just calculating the middle index here, and then just performing a bunch of comparisons and swaps to get the median to index low. Okay, so that's median of 3. Another way we can partition is to use randomized partitioning. Right, so if we use median of 3, it's more likely it's more likely for us to get an n log n time complexity, right? Even with sorted inputs, right? But it is still possible for us to end up with. So it's still possible to give this quicksort variance an input such that it'll end up with an O(n) squared time complexity, right? Such that it'll take O(n) squared time. So another way to partition is to use randomized partitioning, right? Where we use a random number generator to pick a random element to be the pivot, right? And if you do this, then it's kind of impossible, right, to give this quicksort an input that would lead to it taking O(n) squared time, right? Because every time you're choosing a random pivot, so no input is going to consistently cause the algorithm to take O(n) squared time. Right, so here's how you would implement this. So here, before we call the partition function, we're going to pick a random index between low and high. So randint here is just a helper function that chooses a random integer between low and high. Right, and rand here is a library function. provided by stdlib.h. And we swap this element with the element at index low, okay? And then we proceed as normal. So we core partition. Okay. And so those are some quicksort variants, right? And we can even improve quicksort in other ways. So one way is to use insertion sort for small subarrays, right? And the reason we want to do that is because quicksort is actually pretty expensive for smaller arrays because of the recursion, right? Remember, every time we recurse, we have to set up a stack frame, right? The program has to set up a stack frame for the function, and it has to pass down the arguments into the function. And it's pretty expensive for small arrays compared to a simpler algorithm such as insertion sort, right? So one improvement we can make is to use insertion sort for smaller subarrays. Okay, so the way we would implement that is we would have a predefined threshold, right, such as 5, but it could be a larger value like 10. And if the size of the subarray, so high minus low, is smaller than threshold, right, then we call insertion sort instead, right, and then we just return. Okay. So that's one way to implement this improvement. Another way to implement it is instead of calling insertion sort as soon as you have a subarray of a small subarray, what you could do is instead of doing that, you could just return straight away. So you don't sort that small subarray, but after the quicksort is finished, you then go through the entire array and perform one insertion sort. And yeah, so this is probably a slight improvement over the original, so the first version, because you're only calling insertion sort once. Okay, so yeah, that's some improvements you can make to quicksort. Okay, and finally, so how can we quicksort a linked list? So it is possible, and you can do it in a similar way to how quicksort works on arrays. So you can choose the first element to be your pivot, right? And then you can take the rest of your list and sort them so that you have one list that has all the elements smaller than the pivot and another list where all the elements are bigger than the pivot, right? And then you recursively sort both lists. And then now that you have a sorted list where all the elements are smaller than the pivot, and you have the pivot itself, and you have a sorted list where all the elements are greater than the pivot, you can then kind of link them all together, right, to get one full sorted list. Okay, so what I think I'll do is I'll add a diagram for this on the next slide, because there isn't one currently. Okay, so right, we have two algorithms, merge sort and quicksort. So how do they compare? Right, so merge sort has a worst case time complexity of n log n, right, and quicksort has a worst case time complexity of n squared. So you might think that, well, merge sort has to be better, right, because it's faster or more efficient in the worst case, right? But it turns out that because of the way that computers are designed, quicksort actually is faster than merge sort, right? And one reason is that quicksort is more cache friendly. Okay, so this is kind of not kind of less related to algorithms and more related to computer architecture, but modern computers have a cache, right? And what a cache is, it's where when your program accesses a memory address from RAM, right? The cache is going to store the block of memory that address belongs to in the cache, and the cache is much more closer to the CPU than RAM, right? So now when the program tries to access memory addresses close to where the original memory address is, it'll use the cache instead of getting the memory from RAM, and that's much quicker. Okay, and quicksort can take advantage of this because it's an in-place sorting algorithm, right? It doesn't use any temporary arrays. So when quicksort tries to sort a subarray that's small enough that it will fit inside the cache, right? Then it can access the memory much more efficiently, right? Because it doesn't have to go to RAM. It can just take the memory from the cache. Okay, and meanwhile, merge sort uses a temporary array, right? So that's an extra bit of memory that the CPU has to access, and that means it's going to be a bit slower because it has 2 bits of memory that it needs to keep track of now, right? The original array and the temporary array. Meanwhile, merge sort is more easily parallelizable, right? And what I mean by parallelizable is it's easier for it to divide the work among multiple CPUs, right, or multiple cores. So that's because it really evenly splits the array, right? And so what merge sort can do is that it can split the array into 4 equally sized parts, and then get each of the cores to merge sort one of these pieces, right, of the array. Meanwhile, quicksort can't easily parallelize because when you choose a pivot, you don't know where it's going to end up, right? You don't know how big the left half is going to be, how big the right half is going to be. Yeah. Okay, and then here is a summary of the 2 sorting algorithms. So yeah, notice that in the best case and average case, they're both n log n, right? In the worst case, merge sort is n log n, and quicksort is n squared, but quicksort is still faster in practice. Okay, and in terms of stability, merge sort is stable, quicksort is not because of the long-range swaps, and neither of them are adaptive. Okay. So if you're interested in another sorting algorithm, one that you might be interested in is called Tim sort. So Tim, that's the name Tim, so Tim sort. So that's what Python uses for its built-in sort function. And it's a combination of merge sort and insertion sort. Actually, it's a more clever implementation of merge sort that's combined with insertion sort. And Tim sort is adaptive, right? So if you give it a sorted array, then its time complexity will be O(n), which is very cool. Yeah, so if you're interested, you can check that out. All right, but that's it for this part. So this topic. And does anyone have any questions? Yeah. Yeah. So the question was, isn't the best case of these algorithms O1 because if you have an array of size 1 or 0, then the cost will be constant time. So that's not exactly the case because what we're expressing with these time complexities is how long the algorithm takes as the input size grows, right? If we said the best case time complexity was O1, that means regardless of the size of the inputs, the algorithm is always going to take constant time. But that's not the case here, right? If the array is bigger, then the algorithm is going to take longer. In the best case, it's still going to take longer, right, as the input grows. So it's important to remember here that this is a function, right? It's a function of how long the algorithm takes versus the input size. Yeah. Okay. So any other questions? Yep.
So at the end, you said that merge sort was better for linked list. I was wondering why that is.
Merge sort is readily stable, readily parallel, good choice of sorting lists. Okay, so for good choice for linked lists, I'll have to get back to you on that one. But I think it is pretty easy to implement merge sort on linked lists because it's really easy. If you have two sorted linked lists, it's really easy to merge them. But I'll get back to you on the actual reason. Yeah. Okay, any other questions? Okay, so what we'll do now is talk a little bit about non-comparison based sorting algorithms. And these are really interesting because you'd think that in order to sort an array, right, you need to compare the elements, right? But it turns out there are some algorithms where you don't have to compare at all, right? So, though they do come with some caveats. So we'll talk about what those are. Okay, but what we'll start off with is we'll note that all of the sorting algorithms that we've talked about so far have been comparison-based sorts. Right? So they rely on us being able to take two elements and compare them. Right? And they do this over and over again for different pairs of elements until it's able to determine what the correct sorted order is. Right? And what we can show is that these algorithms require big omega of n log n comparisons, right? So this is the kind of only place you'll see big omega, and you don't need to worry about what it means. But what it means is that these comparison-based sorting algorithms require at least k times n log n comparisons for some constant k. Okay, so for a sufficiently large array, these algorithms will need at least k times n log n comparisons in order to sort the array. Okay, so why is that? And the reason is because of the limitations of the information that a single comparison can give us, right? So let's start off by considering an array with 3 items, right? So if we only perform one comparison, right, then obviously we won't be able to sort the array, right? Because we can compare the circle and triangle, so these shapes are just placeholders for values, which we don't know what they are. So say we compare the circle and the square, right? And if that's the only comparison we perform, then there's no way for us to know how big triangle is, right? So we can't sort the items, right? So one comparison isn't enough. And even if we are allowed to do two comparisons, we still can't sort the array, right? And why is that the case? Well, that's because if we have 3 items, right, then there are 6 ways to order them, right? And one of these orders is going to be the correct one, right? It's going to be the sorted one, right? But if we only perform 2 comparisons, then there are 4 possible results of those comparisons, right? So say we compare circle with square, square with triangle, right? There are 4 combinations of results, right? So either both of these comparisons are true, so circle is less than square, square is less than triangle, or one of them, or the first comparison is true, the second one is false, the first one is false, the second one is true, or both comparisons are false. Okay, so 4 possible results, right? But remember we had 6 possible permutations, right? So that means that for some of the results, right, of the comparisons, it's possible for both, so it's possible for more than one permutation to satisfy these results. Right, so for example, if we found out that circle was less than square, right, but this second comparison is false, which means that triangle is less than square, right, then we know that square is the largest element, but we don't know how large the circle and triangle are relative to each other. Right, so it's possible that this permutation is sorted, or this permutation is sorted, right? And same for this this result here. So if it turns out that square was less than circle, right, and square was less than triangle, then we know that square is the smallest. But again, we don't know whether the triangle is bigger than the circle, or if the circle is bigger than the triangle. Okay, so we don't have enough information to deduce definitively which of these permutations is sorted. Okay, and here is the more mathematical explanation. So if we have 3 items, or if we have n items, then there are n factorial ways to order them. Right, so n factorial possible permutations. But if we only perform 2 comparisons, then we only have 2 to the power of 2 groups, right, to put these permutations into, like we did here. So 4 groups, 4 possible combinations of results. Okay, so that means it's possible for one of these results, right, to correspond to more than one permutation. Okay, and that means we need one more comparison, right, in order to sort these elements. Right, so we need 3 comparisons, because what this will do is now we're going to have 8 possible combinations of results. Right, 2 to the power of 3 is 8. And that means each permutation can belong in its own group, right? So each permutation can belong to its own set of results. Okay, so in general, if we have n items, then we have n factorial permutations. If we perform k comparisons, that creates 2 to the power of k groups. And that means in terms of the number of comparisons we have to do, we have to perform k comparisons so that 2 to the k is greater than or equal to n factorial. Okay, so here is some maths to end up with the conclusion that the number of comparisons k is at least or is big omega of n log base 2n. Okay, so you don't have to worry about coming up with this derivation, but you should understand that for comparison-based sorting algorithms, the lower bounds on the number of comparisons you have to do is n log n. Okay, so yeah, so that means the theoretical lower bound on the worst case time complexity for comparison-based sorting algorithms is big omega of n log n. Okay, so the question is, can we do better than this? Well, for comparison-based sorting algorithms, no, right? But if we do away with the idea of performing comparisons, then we can do better. And these algorithms are what we call non-comparison based sorting algorithms. Okay, so yeah, so with non-comparison based sorting algorithms, they do require some assumptions about the data, right? And one such sorting algorithm is called radix sort, and what it assumes is that we can break up the data into symbols, right, or letters. So yeah, what radix sort requires us to be able to do is to break up our keys into digits or characters or bits. Okay, so for example, 372, so this number, we could break it down into digits, right? 372, right? And as another example, the key Sydney, right? We can decompose that into individual letters, right? S, Y, D, N, E, Y. Okay, and what we're going to do is represent each key as a tuple of its symbols. Okay, so K1, K2, K3, all the way up to Km. Okay, so for example, 372 or SYD, NEY. Okay, so for radix sort to work efficiently, we also want to assume that the number of possible symbols is relatively small, right? So in the case of numeric keys and alphabetic keys, that condition is satisfied because we have relatively few number of symbols, right? If it's a numeric key, then we have only 10 possible symbols, right? The digits from 0 to 9. If it's an alphabetic key, then we only have 26 possible symbols, right, from A to Z. Okay, and the number of possible symbols is what we call the radix. Okay, and that's what the name of the algorithm comes from, radix sort. And we use R, capital R, to represent the number of possible symbols. Right, so for numeric keys, R equals 10. For alphabetic keys, R equals 26. Right, and another assumption that we make about radix sort is that the keys have the same lengths. Okay, but if they have different lengths, then that's still okay. What we can do is we can pad them with a symbol, right, to make all the keys have the same length. Okay, and it's and depending on what kind of key we have, you might need to pad them in different ways, right? So for numeric keys, right, you would want to pad the keys with a 0, right? But you want to put the zeros at the beginning, right? If you're dealing with alphabetic keys, then you want to pad them with a blank symbol, but you want to add the padding to the end of the key, right? Because you want to retain alphabetical order. Yeah. Okay, so now the way that radix sort works, so after we've made all of these assumptions, how it works is we're going to perform a bunch of stable sorts. Okay, so we're first going to perform a stable sort on the array using the last letter or the last symbol in each key. So we're going to sort based on the last letter only. Okay, and it's a stable sort, right? And then we're going to perform a stable sort on the second last letter or symbol, and then the third last letter or symbol, and then so on, until finally we perform a stable sort on the first symbol. Okay, so here's a kind of example showing you how we can use radix sort to sort 3-letter words, right? And it's really important that the sorts are stable, right? And that's because, for example, suppose that this last sort here wasn't stable, right? So what we're doing in the last sort is we're sorting by the first character. So what might happen if the sort wasn't stable is since both of these keys have the same first letter C, right, cat and cog, right, we might end up with cog appearing above cat, right, if the sort wasn't stable. Okay, so it's really important that we use a stable sorting algorithm for each of the sorts. Okay, and here is some pseudocode for radix sort. But what I'll do is I have an example, so I'll use that to explain it to you instead. So here's the example. Suppose we have a 3-letter alphabet, right? So our alphabet is just A, B, C, just for simplicity for the example. So R is equal to 3, and we want to sort this array. Right. First thing you'll notice is that the keys have different lengths. Right. So we'll pad the keys with blank characters. So A here we'll pad with 2 blank characters, and CA we'll pad with 1 blank. Okay, so each key contains 3 characters, right? So that means M is going to be equal to 3. Right? So remember, M is the width of each key. Okay, so the way radix sort works is it uses a number of buckets. Okay, so it has 1 bucket for each symbol, and if we're using a padding character like the blank, then we'll also have a bucket for that as well. Okay, and yeah, so we have buckets for each symbol, and when we want to sort by a particular symbol, so in the first step, remember, we want to sort by the last symbol or the last character. Right, so I've highlighted them now, so we've got C, B, A, blank, blank. Right, what we're going to do is we're going to go down the array, and we're going to store each key into a bucket corresponding to its last symbol, to its last character, right? So for ABC, we're going to store this in the C bucket, right, because the last character is C. Right, for CAB, we're going to store this in the B bucket. For BAA, we're going to store this in the A bucket. And then for these 2 keys, we're going to store them in the blank bucket. Right, so A blank blank goes into the blank bucket, and this also goes into the blank bucket. Okay, and then after we've stored all the keys into the buckets, we're going to go through the buckets in alphabetical order. So blank, then A, B, C. And then we're going to store the items back into the array, right? So A blank blank, CA blank, then we'll go to the next bucket, BAA, then CAB, then ABC. Okay, so notice that we haven't made any comparisons, right? We're just storing things into buckets, and then we're just putting them back into the array. Okay, and an important thing about this is that every time we store an item into a bucket, that takes O1 time. And when we're storing the items back into the array, every time we take an item and copy it into the array, that also takes O1 time. Right, that's important for the analysis later. Okay, so now we've sorted all the keys by their last character, by their third character. Right, now we want to sort them by their second character. Okay, so same principle really. So A blank blank, the second character is blank, so we put this in the blank bucket. Right, then CA blank, we put that in the A bucket, then BAA, A bucket, CAB, A bucket, ABC, B bucket. Okay? And now we just copy the items back into the array. So A blank blank, CA blank, BAA, CAB, and ABC. Okay, and finally, so C bucket is empty. And finally, we want to sort by the first character. Right, so this goes in the A bucket, this goes in the C bucket, this goes in the B bucket, this goes in the C bucket, and this goes in the A bucket. And then we're going to store the elements back into the array. And after we do so, the array is going to be sorted. Okay? And I mean, this is really cool because we didn't need to perform any comparisons, right? So now we are done. Okay, so what's the time complexity of radix sort? So we have a number of variables we need to consider, right? First of all, the array has n items, right? N keys. Each key contains m symbols. Okay, so that's the width of each key. And the radix of, so the radix we denote using R, right? And during radix sort, we use R buckets, right? Or R plus 1 if we're using a blank symbol. Okay, so remember, radix sort performs this stable sort m times, right? 1 for each symbol. So in this case, we performed the stable sort 3 times because each key has 3 symbols. Right? And a single one of these stable sorts takes O of n plus r time. Right? So why is it O of n plus r? That's because we needed to copy each key into the buckets. Right? Each time we copy the key into a bucket, that takes O1 time. Since we're doing it n times, that's going to be O of n. And when we're copying the items back into the array, that, well, we need to iterate over all the buckets, right? So that's going to be R, right? But we're also copying all the n items back into the array. So that's n plus R, okay? So a single stable sort takes O of n plus R time, and radix sort does this m times, right? Like I already mentioned. So that means the time complexity of radix sort is O of m times n plus r, okay? But if r is small, as in the case for numeric keys, or alphabetic keys where r is 26, right? That's a pretty small number. then the time complexity would be O of m times n. Right, so if r is a small constant, then we can drop the constant. So we get O of m times n. Okay, and what this means is that radix sort performs better than comparison-based sorting algorithms. Right? So there are some conditions behind this. If the keys are short, right, m is small, and arrays are large. Right? And that's because, remember, comparison-based sorting algorithms, so the fastest they can get is n log n, right? So that's n log n. So for radix sort, the time complexity is O of n times m, right? So for comparison-based sorting algorithms, we have an log n, whereas for radix sort, we have an m, right? Now, if the array gets larger, right, if n gets larger, then log n is going to get larger as well, right? But if the keys remain small, then m is not going to grow, right? So that's why radix sort is better when m is small, so when the keys are short and the arrays are large. Okay, so finally, actually I can show you radix sort. So what I've got here are two programs, merge sort and radix sort, right? And I'm going to run both to compare them. But what I'll do first is, okay, so I'll generate 1 million keys, and I'm going to sort them using merge sort. Okay. So it takes about 0.67 seconds, and if I double the input size, it's going to take a bit more than twice as long, right? So 1.39. Okay, so let's swap over to radix sort and see how much more efficient it is. Right, so it's taking now 0.2728 seconds for 1 million items. And if I double the input size, it's going to take almost exactly double the time, right, 0.55 seconds. Right, so that tells you that its time complexity is linear in terms of the array size. Okay. Okay, and finally, the properties of radix sort. So first of all, because all of the intermediate sorts we're performing are stable, right, as I showed you before, radix sort is stable, right? So that's quite nice. However, it is not adaptive, right? That's because you're performing the same operations, right, regardless of whether the array is sorted or not. You're still going to be copying things into buckets and then putting them back over and over. And it's the same regardless of how the array is sorted. Okay, and finally, it's not in place, right, because we're storing all the keys into the buckets, right? And this is how much additional space we're using, right, in radix sort. So it's O of r plus n, right, r for all of the buckets that we need to create, and n because we're copying the keys into the buckets. Okay, and with that, well, there are some other non-comparison-based sorting algorithms you could look at if you're interested. So there is something called bucket sort. There are other variations of radix sort. So one's called most significant digit. The version that we looked at was least significant digit because we looked at the least significant digit first. And there's also key indexed counting sort and others, right? But with that, that's the end of sorting algorithms. So yeah, that's it. And I just also wanted to announce that there is a console right after this lecture in the comp sci building. So if you have any questions you want to ask about any of the lecture content so far, you can feel free to walk in and ask. But yeah, otherwise that's it. So I'll see you all next week.
We're gonna